ownership of it. I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class. Just ask that you just bless our work today, help us to glorify you, what we do, and just understand more about your creation, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I guess I should prove some more theorems about limits and so forth, right? That probably would be good. And so let me see if I can write up a theorem about like a product rule for limits. I want to write something that encompasses a lot of the different kinds of products that we encounter in applied calculus, right? Like, so let me just kind of over here tell you what I'm thinking about. Sometimes we've got a scalar function, right, times another scalar function. That's one thing. We've got a scalar function times a vector function. We've got a scalar function times a matrix function. We've got a matrix function times another matrix function. We've got a vector function crossed with another vector function. We've got a vector function dot another vector function. We've got, two different things taking values in some vector space where there's some kind of product defined. We've got that kind of function, those kind of products. These are all possible. So I'd like to see if I could state a kind of a product rule for limits that encompasses all of these. So it seems to me what is common to all of these examples is that we're looking at functions, and I want to take the domain of all of these objects to in principle be a vector space. So so I'm going to be thinking about and I'll just use big F as a generic letter, like let F from V to W1 and G from V to W2 be mappings, not necessarily linear, where technically domain of F is a subset of V, and the domain of G is also a subset of V. All right. Both and W1 and W2 are real vector spaces. Now, of course, I allow the possibility here that W1 or W2 could be the complex numbers. That's just a two-dimensional real vector space, all right? But the domain I'm thinking of as real vector spaces. I'm talking about that kind of thing. Although, admittedly, there's not really a wide gulf between the theory of like limits in a complex space and a real space. It's differentiation where there's like the topology, there's not a difference. We don't talk about the real topology versus the complex topology in complex analysis. There's just the topology of the plane. It's differentiation where you start to see the divide in the ideas. Okay, so now, and suppose there exists star, which is a mapping from W1 cross W2 to, well, W3. W3, yet another vector space. All right. And in the interest of not committing some sort of mathematical heresy of some sort I'm not thinking about, let's keep these all finite dimensional. All right. And by star here, I'm going to assume that that is a bilinear product. Meaning that, you know, if we have, for example, x1 plus cy1 comma, times x2 plus times x2, we get x1 times x2 plus c times y1 times y2, x2 rather. And similarly, if we have x1 times, cx2, let's say, cx2 plus y2, well, we get c x1 times x2 plus x1 times y2. Okay, so this would be a bilinear product. Okay. Now,
bilinear just means distributed on both.
Right. Yeah, I'm not assuming, I can't even, is it commutative? Doesn't even make sense. Because I can't even switch the arguments. Like, it's inputting pairs from distinct vector spaces in principle. Now, in the moment that those become the same vector space, then you can ask the question, is it a symmetric bilinear function? Things like that. But it's possible even, so like, my point to you is that this algebraic structure is shared by all of these products. The scalar multiplication, just multiplication of real valued functions, scalar multiplication of a vector valued function, all these examples, they all share this bilinearity. All right? So, my theorem is going to be this. All right? So this is just setup. Then let me find a marker that's worthy of this theorem. One that works. All right, so then if f of x goes to L1 and g of x goes to L2 as x goes to x naught, then f star g of x goes to L1 star L2. Now, I should confess, I have no idea how I'm going to prove this. So, I'm a little scared at the moment. I don't know what to do. Well, I mean, I think about it. There's different approaches we can take. The question then is, does this even fit the context of my definition of limit to start with? Like, what is f star g? So here, f star g, is it the right kind of thing to even ask the question? F star g is a mapping from what? It's a mapping from V to what? Well, to W3. So yeah, to be clear, I'm assuming that V as well as W1, W2, W3, these are all normed linear spaces of finite dimension. All right? So one approach to take here is to take a very calculational approach and characterize the product by its structure constants. So let me just kind of go down that path for a minute, see where that takes us. So my lemma would just be this. If I need some notation here, so I got about 3 different bases going on. Yeah.
And here, star mapping the product. Is it mapping from W1 across W2?
Yeah.
Because what's the input?
So here like x1, y1 in w1, and x2, y2 in w2. Notice I always put 2's on these guys just as my notational, like.
I'm thinking because we're multiplying, we're applying the product to the function.
Right. So, but I'm defining this to be the function defined pointwise by this rule.
Okay.
And so its output is,
Yeah. Okay.
I mean, this is literally equal to f of x star g of x. That's my definition.
Yeah.
And as such, f of x is an element of w1, and g of x is an element of w2. We multiply them, we get something w3. All right. I mean, if you want this to be calculus 1, w1, w2, w3, and v are all just real numbers. Yay, calculus 1. Okay, so here's the thing. If W1 is the span of, I don't really want to put I don't want to put double indices on these, so I'm going to use letters, all right? So I'm going to say, I guess I'll use alphas, alpha sub I equals 1 to M1. And W2 is the span, I'll use beta, beta sub j equals 1 to M2. And W3 is equal to the span of, I guess I'll use gamma, why not? Gamma sub k equals 1 to M3. Then if those are bases for those vector spaces respectively, then given, let's say, C, I, J, K in the reals, such that, here's how it goes, alpha I star beta j is equal to the sum over k of C, I, J, K, gamma k. If you give me constants that specifies the multiplication on the basis, then there exists a unique bilinear extension to star product as described above. All right, but more concretely, this gives me a formula. All right, this gives me a formula. So if I've got like, x, if I've got like x star y, I can write that as the sum over I equals 1 to M1, sum over j equals 1 to M2, sum over k equals 1 to M3 of, well, C, I, J, K, x sub I, y sub j, gamma sub k. Now, skipping a few steps here, right? How I come up with that formula is I use the bilinearity of the product, I pull the constants out, right? And I get rid of the star product by converting to the structure coefficients and the basis of the range of the product. Yeah? But here's the cool thing, right? Is I can let, C equal to the max of the absolute value ofCijk, right? And if I do that, right? If I do that, and again, just for the sake of making the arguments less cumbersome, I'm going to assume we're working with a basis which has been normalized, a normalized basis. So we're going to insist, without loss of generality, right? Because we could, fine, I guess I don't, I'm feeling guilty about doing it. I won't do it. I was thinking about assuming the length of gamma k was 1, but I guess I don't need to do that, right? So, I could define gamma to be the max of the norms of gamma k. All right? And with those in place, I would have the following estimate, see? I would have the norm of x times y by the triangle inequality, right? Well, I guess I could just write this. This is equal to, like the sum. Well, maybe I'm getting too carried away here.
What we're trying to say here is that if we choose two elements on the basis of the OE1 and the OE2, and we product them together, then we can express that as a linear combination of the elements on the basis of what's up.
Okay, let me just, we're getting there. So by the triangle inequality, this is less than or equal to like the sum, and I'm just gonna leave it ijk, okay? With the understanding that those range respectively over m1, m2, m3, yeah? And then, so, I would have the norm of this guy right here, right? I'd have the norm of that, but let me simplify that because I'm out of board. So, since the maximum of these is C, I can put a C here. And then I'd have x of I, y sub j. Those are absolute value. Those are real components with respect to the alpha I basis and the beta j basis respective. And then of course, well, I can trade this out for the max gamma, right? Now, if I'm working with the basis, right, and let's suppose I'm working with the basis that has, remember the property we wanted? We want the ith component of x to be less than or equal to the norm of x, right? We definitely want that property for our norm, at least while improving hard things. So that would make this less than or equal to the sum over I, j, k, c, norm x, norm y, gamma. But then, what are you looking at there? What is that? Is there any ijk dependence to that whatsoever? There's not, right? So if you've got a finite sum over ijk ranging from m1, m2, m3, and you multiply these things out, you've got an m1 nomial, an m2 nomial, an m3 nomial. When you multiply that, you get m1 times m2 times m3 total terms, and it's all adding up the same stupid number. In other words, this is straight up m1, m2, m3, c, gamma, norm x, norm y. And I would point out that we might as well just call this whole giant mess right here, we might as well just define that to be big M. Because it's independent of x and y. You see that? It's independent of x and y. It's just a characteristic of the product that we're dealing with. Like if we're dealing with the absolute value product, that big M is literally equal to 1. And this doesn't need to be inequality. It's just strict. The absolute value of x times y is equal to absolute value of x, absolute value of y. If this is the complex product, if x and y are complex vectors, this product reduces to complex multiplication. You don't even need the inequality. You can replace it with equality. The product of the modulus of the product is the product of the moduli. But generally speaking, we have to content ourselves with some sort of inequality relation to measure the length of a product as it relates to the length of the inputs to the product. So once you have that, once we have this estimate, then all of a sudden the problem of showing the limit exists is not so scary. Maybe we can do it, right? I'm still kind of scared of it though, because I remember how hard it is to prove the product limit even in the case in complex. Hard enough that I didn't do it in class. I mean, I projected it, but excuse me.
The whole point of this lemma was showing that the norm of the product of x and y is less than or equal to
See, having proved this, so the lemma, to summarize, what does the lemma say? It says if you have a product like this, right?
it's bounded by
The lemma simply says there exists M, right, greater than 0, such that for which the absolute value of the norm rather of x times y, right, is less than or equal to M times the norm of x, norm of y. I don't think I've ever done this before, Ernesto. Like this is new for me. So we're discovering this together, but I mean that's a pretty general lemma. It subsumes so many things. Okay, so let's see the theorem. Do we have a chance at the theorem now? Let's just study what we're trying to do. We're trying to come to terms with how to calculate the norm of like f of x star g of x, right? Minus L1 star L2. We'd like that to be less than epsilon, and we have control. What do we control? Well, we control the norm of f of x minus L1, right? And we control the norm of g of x minus L2. And how do we do that? Well, we assume 0 is less than norm of x minus, the point in question, right? Less than like delta f. And we need to have this one less than delta g. So I think I think the regular product rule, it involves like a three-pronged attack, adding 0 in the middle, and choosing like 3 deltas simultaneously to achieve various goals. One of which is bounding one of the functions. The other involves, making difference of the function and its limits appropriately small. But the smallness relates to the choice of the bound. I don't remember it off the top of my head. It's in the complex notes. I have this proof for the product of complex limits. I suspect there's a way to adapt that proof.
We use the triangle inequality and then use this rule and then rearrange and arrive at that.
Well, yeah, I mean, we could do something like this. Let's see here, f of x star g of x. And then I think we want to do something like minus maybe L1 times g of x plus L1 times g of x minus L1 times L2. So that's just equal to the thing above. Then we triangle inequality that. Then we got the norm of f of x minus L1 times g of x plus L1, norm of L1 times g of x minus L2. Which you're right. Then we can use the lemma. That's less than or equal to the big M times, the norm of f of x minus L1 times the norm of g of x, right, plus the norm of L2 times the norm of g of x minus L2. Let me put some parentheses in here. So to finish the thought, because the limit of g of x as x approaches, like we can make this not too big. Trying to think how to do that. If for example, if delta g is less than or equal to 1, then we have the norm of g of x, right, is equal to the norm of g of x minus L2 plus L2, which is less than or equal to the norm of g of x minus L2 plus L2, norm of L2, right? Which is less than or equal to less than 1 by construction. So if we bake this into the cake, so to speak, then we can make this right here. We make this guy less than 1 plus the norm of L2, right? So if we make epsilon, this is less than epsilon f, right? This is less than epsilon g. We have control over those. So maybe I should make my epsilon f like equal to, epsilon over 2, perhaps. Seems too simple. feel like I'm forgetting something here. But anyway, epsilon over 2, 1 plus the norm of L2, yeah, times big M. So that will make all of this collapse to epsilon over 2. And then over here, if I just make epsilon g equals to, this feels too easy, Ernesto. I feel like this feels too easy. But whatever, I'm going to go on. So there I would want like epsilon over 2 m length of L2, right? Modulus of norm of L2. If the norm of L2 is equal to 0, we need a separate argument there that's easier. So otherwise this is troublesome. Although I probably could dress that up by like adding 1 or something smart. I'm not going to be smart, I'm just going to leave it like that. So if I do that, if I assume I've got delta F and delta G such that it imposes this, and then I let delta equal to the minimum of 1, my delta F and my delta G, right? Like that. Then effectively I have delta G less than 1 in that way of thinking. So I get all of these constraints, and this is just less than epsilon. And so subject to those choices of delta, I can make that less than epsilon. Yeah. Now the other way to prove this is just this. So this is like the smarter way for me to prove it, in some sense, because no epsilonics, but like f of x times g of x. Well, that's just equal to the sum over I, j, k, ci, j, k, f sub I, g sub j, gamma sub k, all of this. Well, fine, let me not write that. F sub I of x, g sub j of x, all right, gamma sub k. That's a formula. It's true from the whole discussion over there. If I assume that the limit of f of x is L1, and if I assume the limit of g of x is L2, by the vector limit theorem we proved last time, this, that means that fi of x must map to L1, well, L1 sub I, if you will, where I'm assuming that L1 is like the sum over L1 sub I of alpha I equals 1 to M1, right? And likewise, g sub j of x maps to L sub 2 sub j by the vector limit theorem, where L sub 2 is the sum over j equals 1 to M2 of L sub 2 sub j of beta j. So you see, I know that the component functions converge to the components of the limit. Consequently, by the vector limit theorem, I know that this just maps to the sum over ijk of cijk, L sub I, L sub 1 sub I, L sub 2 sub j, which is gamma k, which is straight up equal to L1 times L2. And the arrow in the middle, what am I using? I'm just using that's where the rubber meets the road right there. So there, see, right here, I need the product. I need the limit of the product is the product of the limits for real valued functions of a vector space. So that's where the sleight of hand is in here, because that is maybe a theorem you've never proved before, that the product, so here x is a variable from a from a finite dimensional vector space? How do I know that real valued functions of a finite dimensional vector space satisfy the limit of a product as the product of the limits? Well, there I really can just replicate the proof that's in the complex notes, because I just replacing, like, it's even easier than that because it's not complex modulus, it's just absolute value for the output. We're talking about real value things. And then of course you're applying that product rule a finite number of times across the sums using additivity of the limits. And so I don't know, like, which is the better way of arguing, like up here or down here? They have their place. Okay? Yeah, yeah. Excuse me. All right, so anyway, now that we've done this, let us agree that we can calculate limits using the product rule, and we don't have to prove it again. Whew. Although I would anticipate we will prove the product rule for derivatives again when that happens. But let me see how much time I burnt on that. Hey, that wasn't too bad. Only cost us a half hour and change. Okay, almost 40 minutes. All right, so any questions? What should we do next as we're thinking about this? We're trying to develop analysis on norm linear space, right? So we have limit laws. Oh yeah, we could go on and do that. Well, I'm just trying to make sure I have done all the legwork I'm supposed to do here. Trying to think of, oh, I know something that we could look at right now. This would be kind of tied into this, but different. Just before we hit the derivative. So here's just an example. Example, what am I on? Oh, example 1. If, let's say, A is an element of Rn by n, then we define, the e to the ta as equal to the sum n equals 0 to infinity. Oh, I shouldn't use n here. I should use, like, let's say j. J equals 0 to infinity of t to the j, a to the j, divided by j factorial.
Is this a matrix exponential?
Yeah, this is the matrix exponential. Now, this is, and I'm putting the cart before the horse here, in the sense that we haven't even shown this thing converges yet. So I want to discuss the convergence of the matrix exponential, because I think what we just did bears on it. All right, so how do you define this? How is this technically defined? This means the limit as, let's say, I'll use n goes to infinity. I'm sorry. I'm gonna make this a big n by n just to avoid, like, I'm annoyed. I want to use n. Okay, so, but I don't want it to be the dimension of the matrix. So anyway, n goes to infinity of the sum j equals 0 to n, of course, of t sub t to the power j, a to the j, divided by j factorial, right? So in other words, we define a series of matrices to exist if the limit of the sequence of partial sums exists, right? And I guess that begs the question, what do I mean by sequential convergence, in a norm linear space? So So let's just talk about that. If we've got v sub n equals 1 to infinity sequence in normed linear space V, right? Then Vn goes to, let's say, V in V, if and only if what? For each epsilon greater than 0, there exists delta. Delta? What's wrong with me? Is that where we are? I don't even know what time it is, right? Good grief. Yes, yes. And now I regret my using big N up here, so I'm going to have to say there exists a K. There we go. With feet. A K in the natural numbers, such that N greater than, or it doesn't matter. You can put the equals or not. I'll just say greater than. If I'm greater than K, implies the norm of Vn minus V is less than epsilon. Right? In other words, we can go sufficiently far out in the sequence to make the values of the sequence sufficiently close as we'd like to the limiting value, the limit of the sequence. Okay. Theorem. A normed linear space is complete. Now that's not true in general, but theorem, a finite dimensional normed linear space over R is complete. What's that?
If it's, you said it's not true in general.
Is it
No.
because of the field or because of the...
Because of the field. And I'm not sure, honestly, about, I think there is issues with the finite infinite dimensions as well. My brother was telling me about, he read the book by Gouveia on p-adic analysis, and there's an interesting story there in terms of the relation of the p-adic numbers and their completion and their algebraic closure. Like there's, I feel like that's relevant to this, but in our context, we're a finite dimensional normed linear space over R, it's complete, meaning that Cauchy implies convergent, right? And the proof of that is nearly identical to the one you gave in complex. In complex, you did it for 2 dimensions. Here, you replicate that argument, except for breaking the vector sequence into its component sequences. And you simply argue that if you have the Cauchy condition for the vector sequence, see, if you have this, right, for m and n larger than some k, right? Then that implies that the norm, the absolute value of Vm, the ith component of it, is less than or equal to the norm is less than epsilon. So for that same k, we get that the, Vn sub I, n equals 1 to infinity, is Cauchy in R. Aha! Therefore, it converges because we know the real numbers are complete. Because of course we prove that in real analysis in gory detail. And hey, I've never seen what's actually done in there, so I can claim whatever I want. But I probably wouldn't prove it either. Anyway, so since that's Cauchy in R, that implies that Vn sub I converges to like V sub I for all I, right? And I'm assuming n is the dimension of my vector space all of a sudden, right? Maybe I should just put dimension of V there.
That was the best question, I think.
Ah. And so then you see, well, okay, so then since you have all of these convergent limits, then that pretty much tells you, oh, so I should have then say that the given Cauchy sequence in the norm linear space must surely converge to what? The vector formed by just taking a linear combination over the basis that we're working with of the real limits. And indeed, you can prove that that converges by the vector limit theorem again. So that is a homework problem in my advanced calculus course, and I would encourage you to work through it. It's healthy. It's an easy problem now that you've had this. It's a very easy problem, but it's important to know it because we use it. I don't know if we use it, like, what do we use more than the vector limit theorem? Man, I don't know. Vector limit theorem is just, it's everywhere. Okay, so Cauchy. It's complete. This is a complete space. So in particular, n by n matrices, complete space. All right? So, all right. Wonderful. I'm going to erase this. And I'm going to erase this. All right, now that we have definitions of the things I've written, let's try to show that. So we're going to look at the sequence, right? So I should probably give this thing a name. Let's call this thing, let's call it S sub n of A, since it's the nth partial sum. I feel like I should put an A there. It does depend on the A matrix, right? Okay, fine. I mean, technically it's also got a T dependence, but you know, all right. So we'd like to show that this sequence, Sn of A, right? N equals, well, 0 to infinity, converges. You know, so that's the question. Why? Because if it does converge, wonderful, that's the matrix exponential, by definition, okay? So to show it converges, what we're going to do is we're going to prove it's Cauchy. So claim Sn A is Cauchy sequence in the n by n matrices. All right, so this proof is going to be kind of like the last one I did. We're going to kind of discover the argument and then just say it in words. I won't write it formally, top-down kind of thing, right? So I'm showing you the scratch work, is one way to say it. So I'm showing you how to get a 1/3 credit solution in like Rails. Yeah.
If the sequence converges, does that imply the series converges?
That's the definition. The series converges only if and only if the sequence of partial sums converges. So that's how we define series converging.
Okay.
So it's 12. Okay, I was seeing that as 120. I was like, wait a minute, what happened to my time? Okay, anyway, it's fine. So we want to look at something like, you know, basically we want to study the norm of like S m minus Sn, right? I seem to have dropped the A. You'll forgive me. Okay. We want to study that for m greater than n, right? That's what that's what we're after. What is that? Well, you see that is the sum j equals 0 to m t sub j a upper j to the over j factorial, right? Minus the sum over j equals 0 to n of t sub j, a sub j over j factorial. Maybe this doesn't have anything to do with that lemma. Oh well. It's still good for us to do it. How does that simplify?
The elements have to.
Right, so m greater than, which means that this contains all of that and then some. So this straight up, just by the usual laws of like how finite sums are constructed, that was the sum j equals n plus 1, thank you, to m of t to the power j, a to the power j over j factorial, like so. Now, okay, I guess, yeah. So check this out. A squared, right? What's the norm of a squared? Well, it's the norm of AA, right? The matrix product is a bilinear product. So by my lemma, this is less than or equal to m times the norm of A squared.
But isn't that equal to the norm?
No, it's not equal.
I'm using the rule in the complex module.
Well, yeah, in the complex it's equal to the product, but not here.
Okay.
It is true. There, you can actually do better in this context, Ernesto. It is true, in fact, that with respect to the Frobenius norm, we have this. That is, in fact, true for the Frobenius norm, which is to say that the n by n matrices are actually not just a normed linear space, they're a normed linear space with a product which satisfies that condition. That actually makes, I haven't buried the lead here. When a normed linear space is complete, we say it's a Banach space. Complete normed linear space. Good grief, I didn't already tell you that. Complete normed linear space equals Banach space. Now the interesting Banach spaces, of course, are infinite dimensional, but I like my finite dimensional Banach spaces just the same. Now, n by n matrices, they're not just a Banach space, they're also a Banach space with a product where the norm satisfies this condition. That actually makes the n by n matrices what's known as a Banach algebra. But my point to you was, if we just use my super lazy, greedy lemma at the start of class, you could just say that this is less than m times that.
Yeah. So
But we can do better, in fact. In fact, it's true that the norm of a to the power k is less than or equal to the norm of a to the power k. Yeah. That is, in fact, an estimate we have. So here, this is less than or equal to, by the triangle inequality, the sum j equals 1 to n plus 1. I suppose absolute value of t to the power j divided by j factorial, all right? And then norm of a to the j, but I'll go ahead and use that. So we have norm of a to the power j.
why do we have j equals 1 now?
Oh, that's a good question. I should have put n plus 1. Sorry about that.
And then
Yes. Thank you. Are you with me?
yeah.
So this is nice. Can we control it? So the question then is, what are we looking at? Like, what is that in purple that I just wrote? Well, it's exactly...
Is that the real?
Yeah, it's real. What's it? Yeah, it's related to the real X. Exactly. Yeah. So that would be like e to the what? T, like e to the absolute value of t, norm of a, right? That would be what? That's the sum. Let's say j equals 0 to infinity, right? Of norm of t to the power j, norm of a to the j over j factorial, right?
Yeah.
We know from our study of calculus that that's a convergent series for any t, right? So this converges for all t and a, because the norm of a is finite. And give me any matrix, its norm is finite. I mean, you can make it as big as you want, but for a fixed matrix, it is a finite norm. Okay, so, and likewise for t. So that makes this a convergent. So that means that this has partial sums, which are convergent, hence Cauchy. So that means that this sequence, j equals 0 to, let's say, n of this guy, is Cauchy sequence in the reals. And that's all we need. By this estimate over here, see how that works? We simply say, okay, the blue sequence at the bottom is a Cauchy sequence of real numbers. Therefore, any epsilon greater than 0, I can pick a k sufficiently large that for m and n larger than that k, I can make that, the difference of things in that, as small as I like. But the difference of things in that is exactly this. See, because while I did the difference up here at the level of the matrix calculation, the same calculation can be done down here in terms of the difference of the sums. So this is, in fact, yes. You know, all right, so that's can be made small by the Cauchy condition of that real sequence. And since that can be made small, so can this. Therefore, this is a Cauchy sequence of matrices. Consequently, it converges because Rn by n is a Banach space, and Cauchy implies convergent because it's complete. Therefore, the matrix exponential exists for arbitrary matrix. And I just put the t in there. You know, the t is just cluttering this argument. I'm a dummy, right? Like, check this out, man. Like, this argument would have been like a little bit nicer if I had never written t. You can replace this argument with, like, instead of writing ta, just write a big B. And then at the end of it all, put b equals to ta. Yay. That would be smarter. But I'm interested in e to the ta because I'm interested in the map t maps to e to the ta for fixed a, right? So that's a mapping from, if that's f is a mapping from what? From the, you know, from the reals, right? To the n by n matrices. Sorry. Don't worry, I'll forget about the big N's soon enough. Ay, ay, ay. All right. Let us begin differentiation, right? So we should at least start it today, if that's okay with you. Is that okay with you?
Sure. What?
It is. It is. I'm at the hour mark.
Yeah.
Actually, this is perfect. So the next video starts on differentiation. Woohoo! So we'll go 15 more minutes.